Imagine standing at the edge of infinity. Before you looms a dim, crimson sphere barely visible against the cosmic darkness, yet containing more mass than 300 Earths combined. This isn't the brilliant, life-giving yellow star we call home. This is something far more ancient, far more patient, and far stranger. This is a red dwarf star, the smallest, coolest, and most abundant type of star in the entire universe. Now imagine taking one step forward, then another. The weak gravitational pull barely tugs at you initially, but with each passing moment, it grows stronger. The reddish glow intensifies. Your skin begins to tingle with radiation you cannot see. You're accelerating now, falling faster and faster toward a cosmic furnace that burns at temperatures lower than a welding torch on its surface, yet holds at its heart a nuclear inferno hot, enough to forge the building blocks of reality itself. What happens next will take you through every extreme condition the universe can offer, from the vacuum of space to pressures that would crush diamonds into neutron soup, from temperatures that vaporize tungsten to a fusion core where matter itself transforms. This is not just a journey into a star. This is a journey into the fundamental laws that govern our universe. And by the end, you won't just understand red dwarf stars, you'll understand why they represent both the beginning and the ultimate end of stellar existence in our cosmos. Welcome back to the Cosmic Atlas. Explorers, I'm your guide through the most extreme corners of our universe, and today, we're embarking on perhaps our most intense journey yet. If you're new here, this channel is dedicated to answering the questions that keep astronomers awake at night, and turning complex astrophysics into adventures you can actually visualize. We don't just learn about space here, we experience it. And before we take this terrifying plunge together, do me a huge favor. Smash that like button if you're ready for some mind-bending science. Hit subscribe so you never miss our cosmic adventures. And share this video with anyone who's ever wondered what it would actually feel like to fall into a star. Trust me, by the end of this video, you'll have knowledge that less than 0.1% of humans possess. And you'll see the universe in a completely different light, or should I say, a completely different shade of red. Now, why are we specifically falling into a red dwarf and not, say, our own sun or a massive blue giant? That's actually a brilliant question, and it gets to the heart of why red dwarfs are so fascinating. These stars are the universe's ultimate survivors, while massive stars live fast and die young in spectacular supernovae. And even our sun will eventually expand into a red giant before fading away. Red dwarf stars? They're playing the longest game in cosmic history. Red dwarfs make up approximately 70 to 75% of all stars in the Milky Way galaxy. That means if you could somehow visit every star in our cosmic neighborhood, 3 out of every 4 would be these dim, reddish stellar embers. They're the universe's most common stellar citizens. Yet they're so faint that not a single one is visible to the naked eye from Earth. The nearest star to our solar system, Proxima Centauri, just 4.2 light-years away, is a red dwarf, and you need a telescope just to see it. But here's where it gets truly mind-blowing. While our sun will burn for about 10 billion years total, the smallest red dwarf stars will continue fusing hydrogen into helium for 10 trillion years. That's 1,000 times longer than the current age of the universe. When the last red dwarf finally exhausts its fuel and fades to darkness, the universe will be a cold, dark, and unimaginably different place. Every galaxy will have long since gone dark. Black holes will dominate the cosmic landscape, and those final red embers will be the last natural light sources in existence. These stars have captured the imagination of astronomers and astrobiologists alike, because they represent a cosmic paradox. They're small, sometimes barely larger than the planet Jupiter, yet they're true stars, fusing hydrogen in their cores. They're cool, with surface temperatures sometimes lower than a candle flame compared to other stars. Yet their cores rage with nuclear fire. They're dim, emitting just a fraction of a percent of the sun's light. Yet they can unleash stellar flares 1,000 times more powerful than anything our sun produces. And perhaps most intriguingly, many red dwarfs host planetary systems. The TRAPPIST-1 system, for example, has 7 Earth-sized planets orbiting a red dwarf just 40 light-years from Earth. 3 of those planets orbit in the habitable zone where liquid water could exist. Could life exist around these ancient, stable stars? That's one of the most exciting questions in modern astronomy. But today, we're not looking for life around a red dwarf. We're taking the ultimate plunge into one. We're going to experience every layer, every physical process, and every extreme environment these cosmic dynamos have to offer. We'll feel the radiation, the heat, the impossible pressures, and ultimately, we'll understand what it means to become one with a star. So strap in, fellow explorers. Check your imaginary heat shields, calibrate your impossible physics protective gear, and prepare for a journey that will take us from the cold vacuum of space to the nuclear furnace. At a star's heart, this is what if you fell into a red dwarf star. Let's begin. Before we take our fateful plunge, we need to understand exactly what a red dwarf star is. And I promise you, the reality is far more fascinating than you might imagine. These aren't just small stars or cool stars, they're fundamentally different. From larger stellar objects in ways that completely change how they work, how they evolve, and ultimately, what would happen to you inside one. Let's start with the basics. Red dwarf stars are classified as M-type main sequence stars, sometimes called M-dwarfs by astronomers. They're defined by their mass, anywhere from about 0.075 solar masses, that's 7.5% of the Sun's mass, up to about 0.50 solar masses, or half the Sun's mass. Below that 0.075 threshold, you don't have enough mass to sustain hydrogen fusion, and you get a brown dwarf instead, a failed star that never quite made it. Above 0.50 solar masses, you get into K-type orange dwarf territory, which are hotter and more luminous. To put this in perspective, the smallest red dwarf stars have a mass of about 80 times that of Jupiter, while the largest ones are still only half the Sun's mass. In terms of physical size, we're talking about objects ranging from just 10% larger than Jupiter all the way up to about 60% of the Sun's diameter. The smallest red dwarfs are genuinely tiny on stellar scales. You could fit several of them inside our Sun with room to spare. But here's where size becomes deceiving. Even though red dwarfs are small, they're still phenomenally massive compared to anything in our everyday experience. A red dwarf with just 0.1 solar masses still weighs about 200 nonillion kilograms. That's a 2 followed by 29 zeros. If you tried to count to that number at 1 number per second, it would take you about 6 trillion times the current age of the universe. And all of that mass is compressed into a sphere not much bigger than Jupiter. This extreme density is our first hint that falling into a red dwarf is going to be very different from, say, falling through Jupiter's atmosphere. We're not dealing with a gas giant planet here. We're dealing with a gravitationally bound plasma ball where the matter is so hot and dense that it exists in states completely foreign to anything on Earth. Now let's talk temperature, because this is where red dwarfs get their name and where things get really interesting. The surface temperature of a red dwarf, what astronomers call the photosphere, ranges from about 2000 Kelvin at the coolest end to about 3500 Kelvin at the hotter end. Let me translate that into more familiar units. We're talking about 100 to 5800 degrees Fahrenheit, or roughly 1700 to 3100 degrees Celsius. To give you a sense of scale, the melting point of iron is about 1538 degrees Celsius. The surface of a red dwarf is hot enough to melt iron, turn it into liquid, boil it away into vapor, and then ionize that vapor into plasma. The hottest industrial furnaces on Earth max out at around 1000 degrees Celsius, cooler than even the coolest red dwarf surfaces. Compare this to our Sun, which has a surface temperature of about 5778 Kelvin, nearly twice as hot as the coolest red dwarfs. And massive blue giant stars can have surface temperatures exceeding 30,000 Kelvin. So red dwarfs really are the cool kids in the stellar neighborhood. But don't let the word cool fool you. We're still talking about temperatures that would vaporize any known material instantly. This relatively low temperature is also why red dwarfs are red. Stars emit radiation across a spectrum of wavelengths, but the peak wavelength depends on temperature relationship described by Wien's displacement law. Hotter stars like our Sun peak in the visible light range, appearing yellowish-white. Blue giants peak in shorter, more energetic wavelengths, appearing blue. Red dwarfs, being cooler, peak in the longer wavelengths of the red and infrared portion of the spectrum. In fact, most of a red dwarf's energy output is in the infrared radiation we can't see with our eyes, but can feel as heat. If you could somehow safely observe a red dwarf up close, it would glow a dull orange red, like a cosmic coal that's been burning forever but never quite reaches a bright yellow flame. The light would be dim, eerie, and would cast everything in deep crimson shadows. This brings us to luminosity, how much total energy these stars radiate. And this is where red dwarfs really show their minimalist nature. The smallest red dwarfs emit just 0.01% of the Sun's luminosity. That's 10,000 times dimmer than our Sun. Even the largest red dwarfs only emit about 7 or 8% of the Sun's light. This is why, despite being our nearest stellar neighbors and the most common stars in the galaxy, we can't see any red dwarfs with the naked eye. They're simply too dim. But here's the beautiful irony. This dimness is precisely why red dwarfs will outlive every other type of star in the universe. Stellar lifetime is inversely proportional to mass raised to approximately the 2.5 power. Massive stars burn through their fusion fuel incredibly quickly. A star 20 times the mass of the Sun might only live for 10 million years. Our Sun will last about 10 billion years total. But a red dwarf with just 0.1 solar masses? It will burn for 10 trillion years. Let me repeat that with emphasis, 10 trillion years. The universe is currently only 13.8 billion years old. That means the universe would need to age another 725 times its current age before the first red dwarf stars even begin to run out of fuel. Every red dwarf that has ever formed is still on the main sequence, still fusing hydrogen, still shining however dimly exactly as it has since its birth. Not a single red dwarf has died of old age yet. Not one. This longevity has profound implications. When our Sun dies in about 5 billion years, red dwarfs will still be in their infancy. When the last massive stars blink out and the universe enters, what cosmologists call the degenerate era, red dwarfs will still be burning. They will be the last stars to shine, the final lighthouses in an increasingly dark and cold cosmos. Now that we understand what red dwarfs look like from the outside, let's dive into their internal structure, because this is where red dwarfs reveal their truly alien nature. In larger stars like our Sun, there's a distinct internal structure with different zones. At the Sun's core, nuclear fusion occurs in a region about a quarter of its radius. Above that is the radiative zone, where energy slowly diffuses outward through countless absorptions and ray emissions of photons, a journey that can take 100,000 years or more. Finally, in the outer third of the Sun, we have the convection zone, where hot plasma rises to the surface, cools, and sinks back down in massive circulation cells. Red dwarfs throw this entire structure out the window. Below about 0.35 solar masses, which includes the vast majority of red dwarfs, these stars are fully convective throughout their entire volume. There is no radiative zone. The entire star, from the fusion core to the visible surface, is a churning, turbulent ocean of plasma. Imagine a colossal pot of boiling water. Except the water is ionized hydrogen plasma at temperatures of millions of degrees, and the pot is held together not by a container but by its own immense gravity. Hot plasma rises from the core, carrying energy toward the surface. As it reaches the photosphere, it radiates energy away, cools down, and sinks back toward the center. This convective circulation thoroughly mixes the entire star. This has a profound consequence. While stars like the Sun can only fuse the hydrogen in their cores, leaving huge reserves of hydrogen in their outer layers forever untouched, red dwarfs can access nearly 100% of their hydrogen fuel, as fresh hydrogen is continuously cycled down to the core and helium is mixed upward and outward. The entire star slowly converts its mass from hydrogen to helium over trillions of years. This is another reason for their extraordinary longevity. It's like having a car where, instead of only being able to burn the fuel in the bottom of the tank, you can somehow access every single molecule of gasoline. Red dwarfs are the ultimate fuel-efficient stars. The mechanism of energy generation in red dwarfs is the proton-proton chain reaction, the same fusion process that powers our sun's core, just operating at a much slower, gentler rate. In the simplest form, the hydrogen nuclei protons are fused together through a series of steps to create one helium nucleus, releasing energy in the process according to Einstein's famous equation, E equals mc squared. But here's the catch: fusion requires truly extreme conditions. The protons have to get close enough together within about 10 to 15 meters for the strong nuclear force to overcome their electromagnetic repulsion and bind them together. This requires enormous temperatures and pressures. In the sun's core, temperatures reach about 15 million Kelvin and pressures hit to 150 billion atmospheres. In a red dwarf, conditions are more modest but still utterly extreme by human standards. Core temperatures range from about 2 million Kelvin in the smallest red dwarfs to around 10 million Kelvin in the larger ones. Pressures reach tens to hundreds of billions of atmospheres. These conditions are enough to sustain fusion, but just barely. The fusion rate in a red dwarf's core is much slower than in the sun, which is precisely why they can stretch their fuel supply over such immense timescales. Here's something mind-bending. The energy density in a red dwarf's core, the power output per cubic meter, is actually lower than your body's metabolic rate. A cubic meter of red dwarf core produces maybe 100 watts of power, while a cubic meter of human tissue produces about 1,000 watts through chemical metabolism. The star compensates for this by having an enormous volume of fusing core. It's not burning hot and fast, it's burning cool and slow, like a carefully banked fire designed to last eons. The fully convective nature of red dwarfs also affects their magnetic fields. Larger stars, like the Sun, generate magnetic fields through a process involving the interaction between the radiative and convective zones, what's called the solar dynamo. Red dwarfs don't have distinct zones, but they still generate powerful magnetic fields through a turbulent dynamo process, driven by their convective motions and rotation, and these magnetic fields are anything but gentle. Observations have shown that many red dwarfs have surface magnetic fields, thousands of times stronger than the Sun's average field. These intense magnetic fields store enormous amounts of energy, which can be suddenly released in stellar flares' massive eruptions that we'll encounter in terrifying detail as we approach our target star. The composition of a red dwarf is relatively simple. It's mostly hydrogen, about 73% by mass, and helium, about 25% by mass, with trace amounts of heavier elements like carbon, nitrogen, oxygen, and metals, what astronomers call metallicity. Even though we're talking about all elements heavier than helium, older red dwarfs formed in the early universe have lower metallicity because the universe hadn't yet produced many heavy elements through stellar nuclear synthesis. Younger red dwarfs incorporate more metals from previous generations of stars that have lived and died. This metallicity affects the star's opacity, how easily radiation can escape, which in turn affects its structure and evolution in subtle ways. Before we take our plunge, let's zoom out and appreciate why red dwarfs matter on a cosmic scale. These stars aren't just interesting curiosities. They're fundamental to understanding galactic evolution, the search for extraterrestrial life, and the ultimate fate of the universe itself. First, their sheer numbers make them important. With 70 to 75% of all stars being red dwarfs, they represent the majority of stellar mass in the galaxy. When we look at the Milky Way, we see the bright, massive stars because they're luminous, but the true bulk of the galaxy's stellar population is invisible to the naked eye. A vast sea of dim red stars that outnumber their brighter cousins by 3 to 1. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf. It's part of a triple star system with Alpha Centauri A and B, and it's the closest star to Earth at just 4.24 light years away. Yet even at this cosmic doorstep, Proxima is invisible without a telescope. If this is typical, and it is, then interstellar space is far more densely populated with stars than our night sky would suggest. Many red dwarfs also host planetary systems, and this is where astrobiology gets extremely interested. In 2017, astronomers announced the TRAPPIST-1 System 7, Earth-sized planets orbiting an ultra-cool red dwarf, about 40 light-years from Earth. 3 of these planets orbit in the habitable zone where temperatures could allow liquid water on the surface. There's intense debate about whether planets around red dwarfs could actually support life. On one hand, red dwarfs are stable, long-lived, and provide consistent energy output for trillions of years, plenty of time for life to evolve, even if it takes much longer than it did on Earth. On the other hand, red dwarf planets face several challenges. First, to receive enough energy from their dim host stars, habitable zone planets must orbit very close, often closer than Mercury orbits our Sun. At these distances, tidal forces would likely lock the planet's rotation to its orbit, giving it a permanent day side and night side. Could life survive under a perpetual crimson sky on one hemisphere and eternal darkness on the other? Second, red dwarfs, especially young ones, are prone to violent stellar flares that unleash torrents of ultraviolet radiation, X-rays, and charged particles. These flares can be 1,000 times more energetic than solar flares, and they could strip away a planet's atmosphere and sterilize its surface. However, a strong planetary magnetic field might provide protection, and life could potentially survive in subsurface oceans. These questions remain open, but the statistics are compelling. If even a small percentage of red dwarf planets can support life, and red dwarfs make up 3/4 of all stars, then the universe might be teeming with life around these dim crimson suns, life that exists in environments utterly alien to our sunny yellow star experience. Looking even further into the future, red dwarfs will be the last stars. When we're 1 trillion years into the future, all the massive stars will have exploded as supernovae. Stars like our Sun will have puffed off their outer layers as planetary nebulae and collapsed into white dwarfs. The universe will be a much darker place. But red dwarfs, they'll still be shining. When we're 10 trillion years into the future, a timescale so vast that the universe will be 725 times older than it is now, the smallest red dwarfs will finally begin to exhaust their hydrogen fuel. They'll gradually cool, slowly contracting and cooling until they become white dwarfs, but white dwarfs made of helium, not carbon-oxygen like those formed from sun-like stars. These helium white dwarfs will then take an additional 10,100 years or more to cool completely, eventually becoming black dwarfs, cold, dark stellar remnants that emit no light. By this point, the universe will be in its final stages, dominated by black holes, dead remnants, and the slow, inevitable heat death as entropy maximizes. But for the unimaginably long era before that, red dwarfs will be the universe's lighthouses, dim, patient, and enduring. This is what we're about to fall into, not just a small star, but a representative of the universe's most common, most enduring stellar type. A star that will outlive galaxies, outlive everything we can see in the night sky today, and will bear witness to the universe's long fade into darkness. Now, with a full understanding of what a red dwarf is, we're ready to begin our descent. Let's step off the edge and fall into the cosmic deep. We begin our journey 1 million kilometers from the red dwarf's surface. For perspective, the Sun is about 1.4 million kilometers in diameter. So, we're starting at a distance roughly equal to 3/4 of our Sun's radius. We're already well inside the orbit where Mercury circles our own star. But this red dwarf is smaller, much smaller. Let's say we're approaching a typical specimen with 0.2 solar masses and a radius of about 200,000 kilometers, roughly 30% of the Sun's radius, or about twice the size of Jupiter. From this distance, the star doesn't look like much. It's a dull, reddish-orange disk hanging in space, glowing with about the intensity of a dim light bulb seen from across a dark room. The light it casts is eerie, monochromatic, tinting everything in shades of deep crimson and burgundy. If you held up your hand, you'd see it illuminated in rust-colored light, casting long, diffuse shadows behind you into the darkness of space. The surrounding space is not empty. You're within the star's corona tenuous, super-hot halo of plasma that extends far beyond the visible surface. We'll talk more about the corona later, but at this distance, its effects are minimal. The particle density is so low that it's essentially a vacuum by any reasonable standard, perhaps a few thousand particles per cubic centimeter, compared to the key C, particles per cubic centimeter in Earth's atmosphere at sea level. But you are beginning to feel the star's influence. The gravitational acceleration at this distance, assuming a 0 point to solar mass red dwarf, is about 0.027 meters per second squared. That's about 0.3% of Earth's surface gravity, barely noticeable. You could still kick off in the opposite direction and potentially escape if you had sufficient velocity, but you don't. You're falling, and with each passing second, you're accelerating toward the center of mass. Let's do some physics. Starting from rest at 1 million kilometers, with no resistance, we're still in a near vacuum. You can calculate the time it would take to fall to the surface using Kepler's laws and gravitational acceleration. The math gets complex because gravity increases as you fall closer, but we can approximate it would take roughly 4 to 5 days of continuous freefall before you hit the photosphere, but we're not going to experience it in slow motion over days. Let's accelerate our journey, experiencing it in fast forward while still understanding every moment. As minutes pass in our accelerated reference frame, you're picking up speed. Your velocity climbs from meters per second to hundreds of meters per second. The red dwarf grows larger in your field of view, its dim glow becoming more pronounced. At 500 kilometers halfway to the surface, your velocity is now substantial. You're falling at several kilometers per second, and gravitational acceleration has quadrupled to about 0.108 meters per second squared. The star now dominates your field of view, a massive crimson sphere that fills half the sky. The light is noticeably brighter, and for the first time, you can feel heat on your face. Faint, but real. The infrared radiation washing over you is beginning to warm your skin, like standing near a large bonfire. This is also where you'd start to notice stellar flares, if you're unlucky, or perhaps lucky, since it's one of the red dwarf's most spectacular features. Before we get closer, let's talk about these incredible phenomena. Red dwarf stars are notorious flare stars. While our sun produces flares, sudden, violent releases of magnetic energy that spray radiation and particles into space, red dwarf flares operate on an entirely different scale. These events can increase the star's brightness by several times its normal luminosity and release energies equivalent to millions of nuclear bombs detonating simultaneously. The mechanism is magnetic reconnection. Remember how red dwarfs have powerful magnetic fields generated by their turbulent convective motions? These magnetic field lines get twisted and stressed by the roiling plasma until they suddenly snap and reconnect in a lower energy configuration. The released magnetic energy explosively heats plasma to tens of millions of degrees and accelerates charged particles to near light speed. The result is a stellar flare, a colossal eruption that releases energy across the entire electromagnetic spectrum. Within seconds, the flare emits intense X-rays and ultraviolet radiation. Optical brightness spikes dramatically. Radio waves blast outward, and a coronal mass ejection, a massive bubble of magnetized plasma, can be hurled into space at velocities exceeding 1,000 kilometers per second. For a planet orbiting in the habitable zone close to the star, because red dwarfs are so dim, these flares are potentially catastrophic. A direct hit from a superflare could strip away atmospheric gases, drench the surface in lethal radiation, and possibly sterilize the planet of any surface life. Some red dwarfs flare so violently and so often that their planets are continuously bathed in radiation levels that would make Earth's surface look like a nuclear bunker by comparison. For us, approaching from space, a flare would be spectacular and terrifying. Let's say one erupts as we pass the 400,000 kilometer mark. First, you'd see a brilliant white-blue flash on the star's surface, a small region suddenly glowing thousands of times brighter than its surroundings. The light intensity jumping from dim red to searing white will be like looking at an arc welder, without eye protection, within seconds. The ultraviolet and X-ray radiation reaches you, traveling at the speed of light. If you were somehow protected from the visible light, the invisible high-energy photons would still be lethal. UV radiation would damage DNA and proteins, causing immediate cellular destruction. X-rays would penetrate deep into tissue, ionizing atoms and creating cascades of free radicals that tear apart biological molecules. But that's just the electromagnetic radiation. About 10 to 20 minutes later, depending on the exact velocity the coronal mass ejection arrives. This is a wall of magnetized plasma, billions of tons of ionized hydrogen and helium, laced with accelerated particles moving at a significant fraction of light speed. When this hits you, it's like being sandblasted with atomic nuclei traveling at cosmic velocities. The charged particles interact with any matter they encounter, depositing their kinetic energy through collisions and electromagnetic interactions. Your body or any spacecraft you might be in would be subjected to a radiation dose, measured in tens of thousands of sieverts. For context, a dose of just 5 sieverts is lethal to humans within weeks. We're talking about radiation doses thousands of times the lethal threshold, delivered in minutes. Even the best radiation shielding would struggle. Water, lead, and polyethylene, our best radiation shields, work by absorbing and scattering particles. But the sheer intensity and energy of stellar flare particles can punch through impressive barriers. You'd need meters-thick shielding, and even then, secondary radiation from particles slamming into the shielding material would create a deadly environment inside. But let's imagine, for the sake of our journey, that you have impossibly advanced shielding, some kind of science fiction force field that can deflect or absorb this radiation. You'd still witness the awe-inspiring violence of the event. The plasma cloud would light up as it interacts with the sparse coronal gases, creating auroral displays on scales that dwarf anything on Earth. The magnetic fields within the CME would be strong enough to induce currents in any metallic structures, potentially generating electrical discharges and creating a spectacular but dangerous electrical storm. And then, as quickly as it began, the flare subsides. The bright spot on the star's surface fades back to dim red. The plasma cloud dissipates, scattering into the surrounding space. You continue your fall, now with a profound appreciation for the violent power these cool stars can unleash. At 200,000 kilometers, the approximate radius of our target red dwarf Ur. At what would be the visible surface if you could stop here? But you're not stopping. Your velocity is now enormous, perhaps 100 kilometers per second or more, depending on your exact trajectory. At this speed, you'd cross the distance from New York to Los Angeles in less than half a second. You're moving faster than any human-made spacecraft has ever traveled. The gravitational acceleration here is about 0.4 meters per second squared, roughly for 0.5% of Earth's surface gravity. Still relatively gentle, but accumulating rapidly. More importantly, you've reached the point of no return, not because of gravity. You passed that threshold long ago, but because of what lies ahead. The temperature of the surrounding plasma is rising dramatically, while the star's photosphere is at 2,500 Kelvin, about 2,130 C or 4 over OF in this particular red dwarf. You're approaching through the corona, where temperatures paradoxically spike to over 1,000,000 Kelvin. This is one of astronomy's great unsolved mysteries. Why is the corona hundreds of times hotter than the surface beneath it? The answer involves complex magnetic field interactions and wave heating mechanisms. But the practical effect for you is this: you're entering a region of extreme temperature. However, and this is crucial, the density is still extremely low. Temperature and heat are different things. Temperature measures the average kinetic energy of particles. Heat is the total thermal energy transferred. In the tenuous corona, particles are moving incredibly fast high temperature, but there are so few of them low density that the actual heat transfer is initially Modest dot, it's like the difference between sticking your hand in a 10°C oven, uncomfortable, but survivable for seconds, versus sticking your hand in 100°C water, instant severe burns. The water has much higher density and thermal conductivity, transferring heat far more efficiently. The corona is like the oven, extremely hot particles, but not enough of them to immediately cook you. But that's changing rapidly. With each kilometer of descent, the density increases exponentially. At 150,000 kilometers from the center, 50,000 kilometers above the photosphere, the density has increased enough that radiative heating becomes significant. The infrared and visible light photons pouring off the star's surface are now intense enough to heat any object to hundreds or thousands of degrees Celsius. Your imaginary protective suit is working overtime now, reflecting and radiating away enormous amounts of energy. Without it, your body would be absorbing radiation at a rate that would heat you from 37 Celsius to boiling temperature in seconds. Your skin would char, your blood would boil, and you'd be dead from heat stroke before you even realized what was happening. At 100,000 kilometers altitude, halfway between the corona and the photosphere, you can feel the full intensity of stellar radiation even through your protection. It's like standing on the surface of Mercury at noon, then multiplying that by 100. Every square centimeter of your body is being bombarded by kilowatts of radiant energy. Your suit's cooling system is at maximum capacity, desperately radiating heat away into space before you cook alive. The light is now blindingly bright. What was a dim reddish glow from 1,000,000 kilometers away is now an overwhelming flood of crimson radiance. You can't look at the star directly anymore, even through your visor's protection. The intensity would damage your retinas. The star fills your entire field of view now. There's no more black sky, no more stars, no more reference to the universe beyond. There's only red dot as you cross 50,000 kilometers altitude. The density of the plasma around you increases to levels where you're no longer falling through a vacuum. There's actual matter here, tenuous but real. The drag force, while still minimal at your enormous velocity, is no longer zero. You're beginning to experience the star's atmosphere directly. The temperature of this plasma is dropping as you descend from the million-degree corona toward the cooler photosphere. But cooler is relative. We're still talking about tens of thousands of Kelvin. At 10,000 Kelvin, about 9,700 Celsius or 17,500 F, atomic hydrogen begins to ionize, losing its electron and becoming a plasma of bare protons and free electrons. You're immersed in this ionized gas now, and electromagnetic forces are becoming as important as thermal ones. At 25,000 kilometers altitude, you're in the transition region between the corona and the chromosphere, the layer just above the visible surface. Here, temperature plummets from hundreds of thousands of degrees to tens of thousands of degrees over a relatively short distance. This steep temperature gradient creates spectacular structure spicules, jets of plasma that shoot upward from the photosphere like cosmic fountains, reaching heights of thousands of kilometers before falling back down. If you could somehow survive to observe, you'd see these plasma jets erupting around you, pillars of glowing gas, each one larger than Earth, rising and falling in a constantly shifting forest of fire. The magnetic field lines threading through these structures guide the plasma into beautiful arcs and loops like iron filings, tracing invisible magnetic lines of force. But you don't have time to sightsee. You're still falling at over 100 kilometers per second, and the photosphere is rushing up to meet you. The visible surface of the star, the boundary between transparent and opaque, is seconds away. This is your last moment in anything resembling normal space. Beyond this point, you'll be inside the star, surrounded by matter so dense and hot that all familiar rules break down. The chemistry that defines your body will cease to exist. The molecules that make up your cells will dissociate into atoms. Those atoms will lose their electrons and become plasma. And eventually, even the nuclei themselves will participate in reactions that transform matter itself. You take a final mental breath. The surface rushes up, and you cross the threshold into hell. Although we've been traveling through the corona for most of our approach, now we're experiencing it at its densest and most intense, just above the photosphere. The corona is one of the most mysterious and beautiful parts of any star, and red dwarf coronae have their own unique characteristics that make them both similar to and different from the Sun's corona. First, let's address the elephant in the room, the coronal heating problem. The photosphere of our red dwarf is at about 2,500 Kelvin. Just a few thousand kilometers above it, in the corona, temperatures soar to over 1 million Kelvin. This violates our everyday experience with heat. How does the atmosphere get hotter? As you move away from the heat source, it's like a campfire where the air 10 feet away is somehow hotter than the flames themselves. The answer lies in energy transport mechanisms beyond simple thermal conduction. The leading theories involve magnetic field interactions and wave heating. The convective motions in the star's interior create sound waves and magnetic waves that propagate upward into the atmosphere. When these waves encounter the tenuous plasma of the corona, they dissipate their energy, heating the gas to extreme temperatures. Another mechanism is magnetic reconnection, the same process that causes stellar flares, but on a smaller, continuous scale. The corona is laced with magnetic field lines, and where these field lines reconnect, they release energy that heats the plasma. In red dwarfs, with their powerful and chaotic magnetic fields, this process might be even more important than in the Sun. The result is a plasma environment unlike anything you'd encounter anywhere else. The particles here, primarily protons and electrons, are moving at speeds of hundreds of kilometers per second. That's the meaning of temperature at this scale. The average kinetic energy of particles is equivalent to millions of degrees. But here's the strange part. You could, in theory, pass through the lower corona briefly without instantly vaporizing. Why? Density. At the base of the corona, we're talking about particle densities of key to 1015 particles per cubic centimeter. That sounds like a lot, but it's still a billion times less dense than Earth's atmosphere at sea level. There simply aren't enough particles hitting you per second to transfer lethal amounts of heat immediately. However, not immediately lethal is very different from safe. Radiative heating is still extreme. The photosphere beneath you is blasting photons, upward infrared, visible light, and ultraviolet radiation at intensities that would incinerate any normal material in seconds. And the particles that do collide with you are traveling at such high velocities that each impact delivers enormous energy. But beyond the physical danger, the corona is visually spectacular. If you could somehow observe it without being destroyed, you'd see structures of breathtaking complexity and beauty. Coronal loop arcs of plasma, following magnetic field lines, span distances larger than entire planets, glowing in extreme ultraviolet and X-ray wavelengths. These loops connect regions of opposite magnetic polarity on the surface, creating bridges of million-degree plasma stretching across the star's face. You'd also see coronal holes, regions where magnetic field lines open out into space, rather than looping back to the surface. These holes appear darker because the plasma can escape along these open field lines, reducing the density. Coronal holes are the source regions for stellar wind streams of charged particles that flow away from the star into interplanetary space. And you'd witness the constant flickering and brightening of nanoflares. Tiny flares far smaller than the superflares we discussed earlier, but happening constantly across the surface. Each nanoflare releases energy equivalent to millions of hydrogen bombs, heating small regions of the corona to even higher temperatures. These tiny events may be responsible for much of the coronal heating in the aggregate. The magnetic field strength in the corona is substantial, tens to hundreds of Gauss, compared to Earth's surface magnetic field of about 0.5 Gauss. This is strong enough to dramatically affect the motion of charged particles, forcing them to spiral along field lines rather than moving freely. If your body were ionized down at these temperatures, it rapidly would be the charged particles that once formed your molecules would be constrained to follow these invisible magnetic highways. But you're not staying in the corona. You're falling through it at over 100 kilometers per second, and the density is increasing exponentially with every kilometer of descent. The corona doesn't have a sharp lower boundary. It gradually transitions into the chromosphere below. but there's a region where the temperature plummets from 1,000,000 Kelvin to a few tens of thousands of Kelvin over just a few hundred kilometers. This is called the transition region, and you're entering it now, the chromosphere literally. Color sphere, named because it appears as a colorful ring around the sun during total eclipses, is a thin atmospheric layer between the corona and the photosphere. In our red dwarf, it's only a few thousand kilometers thick, a tiny fraction of the star's radius, but it's where some of the most dynamic phenomena occur. As you descend into the chromosphere, the temperature drops rapidly. We're going from hundreds of thousands of Kelvin at the transition region to about 10,000 Kelvin at the base where it meets the photosphere. This temperature gradient is negative temperature decreasing with depth, which is unusual. Below the photosphere, temperature will increase with depth all the way to the core, following a more intuitive pattern, but density is increasing dramatically. At the top of the chromosphere, we're at about 10-15 particles per cubic centimeter. At the base, densities reach kc particles per cubic centimeter. We're still talking about a near vacuum by Earth's standards, about 1,000,000 times less dense than our atmosphere, but for a stellar atmosphere, this is substantial. There are enough particles now that collisions are becoming frequent, and heat transfer is accelerating. The chromosphere is where hydrogen begins to recombine, where free protons capture electrons and become neutral hydrogen atoms. This process releases energy in specific wavelengths, particularly the H-alpha line at 656.3 nanometers, which gives the chromosphere its characteristic reddish color. If you could observe the chromosphere of our red dwarf in H-alpha light, you'd see it glowing with particular intensity. But the most dramatic features of the chromosphere are the spicules, jet-like eruptions of plasma that shoot upward from the photosphere like cosmic geysers. These structures are about 500 kilometers wide and can reach heights of 10,000 kilometers or more. They last for just a few minutes before falling back down or dissipating into the corona. The driving mechanism for spicules isn't fully understood, but it likely involves magnetic field interactions and shock waves propagating up from the convective motions below. Imagine a garden hose that's been kinked and suddenly released. A pulse of water shoots out at high velocity. Spicules are similar, except the water is plasma at 10,000 to 20,000 Kelvin, and the hose is a magnetic flux tube channeling the flow. As you fall through the chromosphere at your tremendous velocity, you'd be punching through these spicules like bullets through rain. Each one you pass through subjects you to a brief but intense blast of denser plasma. The drag force on your body is increasing now, not enough to slow you significantly yet, but enough to begin generating heat through friction. And here's where things start to get really destructive for anything organic. At chromospheric temperatures and densities, any complex molecules are disintegrating. The chemical bonds that hold proteins together, hydrogen bonds, disulfide bridges. Van der Waals forces are overwhelmed by thermal energy. Amino acids break apart. DNA, if any had somehow survived the radiation up to this point, unzips and fragments your cells, if they haven't already been destroyed by radiation damage, are experiencing complete structural failure. Cell membranes disintegrate as lipid molecules break down. The water that makes up most of your body is dissociating into hydrogen and oxygen. At around 3000 Kelvin, water vapor starts to break down. How becomes H's plus O? At higher temperatures, even molecular hydrogen dissociates. H becomes to H. By the time you reach the base of the chromosphere, you're no longer a human body in any meaningful sense. You're a cloud of increasingly ionized atoms: carbon, nitrogen, oxygen, hydrogen, phosphorus, sulfur, and trace elements held together loosely by your rapid descent through the plasma, but fundamentally disintegrating into your constituent atomic components. The photosphere is directly below you now. Through the thinning chromosphere, you can perceive the surface, though surface is a misleading term for a gaseous sphere. What you're seeing is the layer where the star transitions from transparent to opaque, where the density becomes high enough that photons can only travel a short distance before being absorbed and re-emitted. You cross into the photosphere at an altitude we'll call 0, our reference level. Though there's no solid surface here, The temperature is about 2500 Kelvin to 1130 Celsius or 1040 F. The density is around kc to kc particles per cubic centimeter, still 1,000 times thinner than Earth's atmosphere, but opaque because the path length through the stellar atmosphere is so enormous. This is what we see when we look at a star, the photosphere. It's the layer from which photons can escape directly to space without being reabsorbed. Below this level, the star is opaque. Photons produced in the interior undergo countless absorptions and ray emissions, taking a random walk that can last thousands of years before finally reaching the photosphere. And escaping. The photosphere isn't smooth. Like Earth's atmosphere has clouds and weather patterns, the photosphere has granulation, a cellular pattern created by convection. Hot plasma rises in the center of each granule, which can be thousands of kilometers across, cools by radiating energy into space, and sinks at the edges. On the Sun, granules look like rice grains covering the surface. On a red dwarf, the granules are larger relative to the star's size and churn more slowly due to the lower gravity and energy transport rates. You're falling through this convective layer now, and it's like descending through a boiling liquid, except the liquid is ionized hydrogen plasma, and the bubbles are thousands of kilometers across. The temperature fluctuates by hundreds of degrees as you pass through rising hot regions and sinking cool regions. The density, however, is steadily increasing. The pressure at the base of the photosphere is about 0.1 atmospheres, similar to Earth's atmospheric pressure at an altitude of about 15 kilometers, around 50,000 feet. You might think that's not so extreme, but remember the temperature. Everything is at 500 Kelvin minimum. At this temperature and pressure, all matter is fully gaseous. There are no solids, no liquids, everything is plasma or gas. The light around you is intense and uniformly red-orange. Every direction glows with the same intensity because you're surrounded by radiating plasma. There are no shadows here, no directional lighting, just omnidirectional radiance. The photon density is so high that radiation pressure, the physical force exerted by light itself, is becoming significant. The atomic and molecular processes happening at this depth are fascinating. Neutral hydrogen atoms are constantly being excited by collisions with free electrons and other atoms, then emitting photons as they return to lower energy states. It's these emission and absorption processes that give the photosphere its spectrum, the characteristic pattern of bright and dark lines that tells us the star's composition, temperature, and motion. If any trace of your original molecular structure remained, it's gone now. Every organic compound has been reduced to simple atoms and ions. The calcium from your bones is ionized calcium. The iron in your blood is ionized iron. The carbon that formed the backbone of every biomolecule is now just carbon atoms and ions, indistinguishable from the carbon in the star's original composition. But you're not lingering in the photosphere. Your velocity, while reduced somewhat by the increasing drag, is still tens of kilometers per second. The photosphere is only a few hundred kilometers thick. You cross it in seconds of subjective time, and below it, conditions become truly extreme. As you sink beneath the photosphere, the light doesn't fade, it intensifies. You're no longer seeing light that's escaping from the star's interior. You're immersed in the light that's trapped, constantly being absorbed and ray-emitted, creating a radiation field of incredible intensity. The temperature begins to rise. 3,000 Kelvin, 4,000 Kelvin, 5,000 Kelvin. Pressure increases correspondingly. 1 atmosphere, 10 atmospheres, 100 atmospheres. Density is skyrocketing. The plasma is becoming thicker, more viscous-like, though it's still technically a gas by phase diagram standards. You're passing through the region where convection is king. Giant circulation cells rising, cooling, sinking, heating dominate the energy transport. These convective cells can span tens of thousands of kilometers and cycle over weeks or months. You're a tiny speck caught in a cosmic conveyor belt of plasma. The drag force is now enormous. At these densities, even at reduced velocity, you're experiencing friction heating that would vaporize any normal material. The atoms that once formed your body are being scattered and mixed into the stellar plasma. Some are carried upward in rising convective streams. Others continue the descent with you into the depths. There's no going back now, there never really was. But now it's absolute. The pressure above you is so immense that even if you could somehow halt your descent, you couldn't rise. The buoyancy of your component atoms is nil. They're the same density as the surrounding plasma. You're part of the star now, subject to its internal dynamics, falling inexorably toward the core. The boundary between the photosphere and the interior is behind you. You're inside the star, and the real journey into extremity is just beginning. In a star like our Sun, the convection zone is just the outer 30% or so, above a radiative zone where energy transport is dominated by photon diffusion. But our red dwarf is fully convective. From the photosphere all the way down to the fusion core, the entire star is churning, mixing, cycling plasma in an enormous convective engine. This has profound implications for your descent. You're not falling through stratified layers with clear boundaries. Instead, you're sinking into a turbulent ocean where local conditions vary dramatically. But the overall trend is clear. Deeper means hotter, denser, and higher pressure. At a depth of 10,000 kilometers below the photosphere, about 5% of the radius into the star, conditions are solidly extreme by any reasonable standard. Temperature has climbed to about 100,000 Kelvin. Pressure is around 10,000 atmospheres, equivalent to the pressure at 100 kilometers depth. In Earth's oceans, except instead of cold water, you're in hydrogen plasma hot enough to emit X-rays. At these temperatures, every atom is fully ionized. There are no neutral atoms left, only bare nuclei and free electrons. The plasma is so hot that the electrons are moving at speeds of thousands of kilometers per second, a significant fraction of the speed of light. The ions, being much heavier, move more slowly but still zip around at hundreds of kilometers per second. This is a regime where classical thermodynamics meets quantum mechanics in interesting ways. The electrons are close enough together and energetic enough that quantum effects become important. Degeneracy pressure, the quantum mechanical pressure arising from the Pauli exclusion principle, is starting to contribute to the total pressure. Though it's not yet dominant as it would be in a white dwarf, the density at this depth is about 10 grams per cubic centimeter, 10 times the density of water. The star is becoming genuinely dense. For comparison, Earth's average density is 5.5 grams per cubic centimeter, and lead has a density of 11.3 grams per cubic centimeter. You're in plasma that's as dense as heavy metals, except it's at 100,000 degrees and consists of independent nuclei and electrons. The magnetic fields threading through this region are twisted and complex. The convective motions, giant circulation cells rising and falling, are constantly stretching, twisting and reconnecting magnetic field lines. Local field strengths can reach thousands of Gauss. If your component atoms are still ionized, and they are, they're being deflected by these magnetic fields, spiraling along field lines in complex helical paths. But the general trend is still downward. Gravity pulls toward the center, and the convective flows, while turbulent, have a net component that carries material toward the core before it heats up and rises again. You or the atoms that were you are caught in one of these downward streams, descending into the increasingly dense interior. At 50,000 kilometers depth, 25% of the radius conditions are becoming truly alien. Temperature, 500,000 Kelvin. Pressure, 100,000 atmospheres. Density, 50 grams per cubic centimeter, 50 times water density. At this temperature, the typical thermal energy of particles is about 50 electron volts. To put that in perspective, chemical bonds typically involve energies of a few electron volts. The binding energy that holds a hydrogen atom together, the ionization energy, is 13.6 electron volts. We're well beyond the point where atoms can exist. Even highly ionized heavy atoms would be stripped of most or all of their electrons. At these energies, the photon field is incredibly intense. Photons are constantly being emitted and absorbed, creating a thermal bath of radiation. The mean free path of a photon, the average distance it can travel before being absorbed, is just a few centimeters at these densities. Light produced in the core takes tens of thousands of years to random walk its way to the surface through countless absorptions and ray emissions. The Sound speed, the speed at which pressure waves propagate, is about 10 to 20 kilometers per second at this depth. That's 50 times faster than sound in Earth's atmosphere. If you could somehow produce a sound here, a meaningless concept. But bear with me, its pitch would be far into the ultrasonic range, undetectable by any human ear. The viscosity of the plasma is also changing. Normally, we think of gases as having low viscosity, they flow easily. But as density and temperature both increase, the plasma starts behaving differently. Collisions between particles become frequent. Magnetic fields resist shear flows. The combination creates an effective viscosity that makes the plasma flow more like thick oil than thin air, at least in certain contexts. The convective velocity is the speed at which plasma rises and falls in the circulation cells, are about 1 to 10 meters per second at these depths. That might not sound fast, but remember the scale. A convective cell might be 50,000 kilometers across and take months to complete a full circulation cycle. The total energy transported by these flows is immense, equivalent to millions of nuclear power plants worth of power. You're deep inside a nuclear furnace now, though you haven't reached the region of active fusion yet. The atoms that composed your body, carbon, oxygen, nitrogen, hydrogen, are completely mixed into the stellar material. Some of your hydrogen atoms might eventually make it back to the surface in a rising convective stream, spend a few months cooling and radiating energy from the photosphere, and then sink back down again. They'll repeat this cycle millions of times over the star's lifetime. At 100,000 kilometers depth, 50% of the radius. Halfway to the center, you're entering the inner regions, where conditions approach those needed for nuclear fusion. Temperature, 1 million Kelvin. Pressure, 1 billion atmospheres. Density, 100 grams per cubic centimeter, 100 times water. Denser than uranium metal, 19.1 grams per cubic centimeter. At 1 million Kelvin, the typical thermal energy is about 100 electron volts. This is getting into the range when nuclear reactions can begin to occur. Though still not quite hot enough for efficient hydrogen fusion, the proton's hydrogen nuclei are moving at about 500 kilometers per second. Their kinetic energy enormous by everyday standards. But there's a problem. Protons have positive electrical charge and, like charges, repel. To fuse two protons together, you need to bring them within about 10 to 15 meters, 1 femtometer of each other, where the strong nuclear force can overcome electrostatic repulsion and bind them together. The electrostatic barrier, what physicists call the Coulomb barrier, requires energies of about 1 MeV, million electron volts, to overcome classically. At 1 million Kelvin. Average particle energies are only about 100 electron volts, 10,000 times too low. So, how does fusion happen? The answer is quantum tunneling. In quantum mechanics, particles don't have definite positions. They have probability distributions. Even though a proton doesn't classically have enough energy to overcome the Coulomb barrier, there's a small but non-zero probability that it will quantum mechanically tunnel through the barrier and end up on the other side, where the strong force can bind it to another proton. This tunneling probability is extremely low for any given collision, but at stellar densities, there are so many protons colliding so frequently that even the tiny tunneling probability results in a significant fusion rate. This is how stars work their quantum mechanical engines, running on the probabilistic laws of the subatomic world. At 150,000 kilometers depth, 75% of the radius, you're definitely in the fusion zone now. Temperature, 2 million Kelvin. Pressure, 10 billion atmospheres. Density, 130 grams per cubic centimeter. Fusion reactions are occurring all around you, or rather, all around the ions that were once part of you. The proton-proton chain is operating. In the first step, two protons collide, and through quantum tunneling and the weak nuclear force, one of the protons converts into a neutron via beta plus decay, creating deuterium heavy hydrogen, a positron, and an electron neutrino. This is an incredibly slow process. The average proton in a red dwarf's core will wait billions of years before undergoing this reaction. but with 1,056 protons in the core undergoing quadrillions of collisions per second each. Enough reactions occur to release a steady stream of energy. The deuterium nucleus quickly fuses with another proton to form helium-3, releasing a gamma-ray photon. Finally, the helium-3 nuclei collide and fuse to form helium for normal helium, releasing two protons back into the mix. The net result, for protons in, one helium nucleus out, plus energy in the form of gamma rays and neutrinos. The energy released per reaction is about 26.7 mevatiny amount by human scale standards, about 4.3 times 10⁻12 joules, but enormous on a per atom basis. This energy is about 0.7% of the rest mass energy of the four protons, per Einstein's E equals mc. Over time, as the star converts hydrogen to helium, it's directly converting mass into energy. The gamma rays produced by fusion immediately collide with the dense plasma, being absorbed and re-emitted countless times. Each absorption slightly reduces the photon's energy, converting it from a high-energy gamma ray to lower-energy X-rays, then ultraviolet, then visible light, then infrared. By the time this energy reaches the surface, tens of thousands of years later, each original gamma ray has been split into billions of lower-energy photons. The neutrinos, however, barely interact with matter at all. They're produced in the weak force reactions of the proton-proton chain, and they simply fly out of the star at nearly the speed of light, carrying away about 2% of the fusion energy. These neutrinos pass through the entire star through the billions of atmospheres of pressure, and the 200,000 kilometers of dense plasma as if it weren't even there. Within 2 seconds of being produced in the core, they're in interstellar space. If any of the hydrogen nuclei that were once part of your body undergo fusion, they'll experience this transformation to protons that were once in a water molecule in your cells, will quantum tunnel through the Calm barrier, fuse into deuterium, and release energy that will eventually tens of thousands of years later warm a planet, or light up the stellar photosphere. In a very real sense, you've become part of the star's energy generation mechanism. Finally, you reach the innermost core within the central 25% of the radius, where 50% of the star's mass is concentrated. This is the heart of the red dwarf, where fusion is most active and conditions are at their most extreme. Temperature, to 0.5 to 3 million Kelvin. Pressure, 50 billion atmospheres. Density, 150 grams per cubic centimeter or higher 150 times the density of water, about 8 times the density of lead. To appreciate this density, if you could somehow extract a cubic centimeter of core material and bring it to Earth keeping it at room temperature, which would require impossible physics, it would weigh 150 grams, about as much as a small smartphone. But that cubic centimeter would contain about kd protons, and electrons 10 trillion particles. The pressure of 50 billion atmospheres is difficult to conceptualize. Earth's atmospheric pressure at sea level is about 101,325 pascals, or 1 bar. 50 billion atmospheres is 5 times kPa. This is the pressure at the bottom of an ocean 500,000 kilometers deep an ocean. That would fill most of the volume between Earth and the Moon, except instead of water. It's ionized plasma at millions of degrees at these pressures and densities. The plasma is entering a regime where degeneracy effects become significant. The Pauli exclusion principle states that no two fermions particles with half integer spin, like electrons and protons, can occupy the same quantum state. As you pack more and more electrons into a smaller volume, they're forced into higher and higher energy states, creating degeneracy pressure that has nothing to do with temperature, and everything to do with quantum mechanics. In a red dwarf, electron degeneracy pressure contributes perhaps 10 to 20% of the total pressure in the core, with the rest coming from thermal pressure, the kinetic energy of particles, and radiation pressure, the pressure exerted by the intense photon field. This is nowhere near the total degeneracy you'd find in a white dwarf, where electrons are packed so tightly that degeneracy pressure is the dominant support mechanism. But it's a hint of the quantum mechanical effects that dominate in even more extreme environments. The fusion rate in the core, the power density. or energy released per cubic meter per second, is actually quite low by everyday standards. It's only about 100 watts per cubic meter, roughly comparable to the metabolic heat production of human tissue. But the core volume is enormous, about 1019 cubic meters, so the total power output is about kc watts, or 1/10 the sun's luminosity. This low power density is why red dwarfs can last so long. They're not burning their fuel aggressively, they're sipping it slowly, extracting every last bit of fusion energy over time scales that dwarf the age of the universe itself. At the very center, the absolute core conditions max out for this particular red dwarf. Temperature might reach 3 million Kelvin. Pressure could hit 100 billion atmospheres. Density might peak at 200 grams per cubic centimeter. This is as extreme as a red dwarf gets, and while it's intense, it's modest compared to the cores of massive stars, where temperatures exceed 100 million Kelvin, and densities can reach thousands of grams per cubic centimeter. The atoms that were once you are now part of this fusion core. Your hydrogen will slowly fuse into helium over billions of years. Your heavier elements, carbon, nitrogen, oxygen, won't fuse at all. The temperatures here are far too low for carbon fusion, which requires tens of millions of Kelvin. These atoms will simply remain in the core, being cycled through convective circulation, possibly making their way back toward the surface over millions of years. In a larger star, heavy elements produced in the core would eventually be enriched and possibly expelled in a supernova, seeding the interstellar medium with the building blocks of planets and life. But red dwarfs never go supernova. They'll burn steadily for trillions of years, gradually converting hydrogen to helium, until finally, in the unimaginably distant future, they'll cool into helium white dwarfs gold, dead remnants that will persist until the very end of time. Your atoms, incorporated into this red dwarf, will share that fate. They'll cycle through the star's convective zones. They'll participate in fusion reactions or simply be bystanders. They'll spend trillions of years as part of this slowly burning ember, and when the star finally dies, they'll be locked into a white dwarf, a cosmic fossil that will outlast everything. This is your ultimate fate. You haven't just fallen into a star, you've become part of its story, a story that will stretch across time scales so vast that the entire history of human civilization, from the first stone tools to the present day, is less than a single heartbeat in the star's lifespan. Let's step back from the experiential narrative and analyze exactly what forces destroyed you. During this journey, we'll start with gravity, the fundamental force that pulled you into the star in the first place. Gravitational acceleration at the surface of our 0 point to solar mass. 200,000 kilometer radius red dwarf can be calculated using Newton's law, G equals gmr, where g is the gravitational constant, m is the star's mass, and r is the distance from the center. For our red dwarf, m equals 0 point to times 1.989, 1030 kilograms equals 3.978, 1029 kgr equals to 100,000. Km equals to times kng equals 6.67 for times 10 to 11 cubic meters. Kg s squared. This gives us g approximately equals for 140 meters per s squared. At the surface, about 45 times Earth's surface gravity. That's intense, but not impossible to comprehend. Fighter pilots can briefly withstand accelerations of 9 Gs with special suits. 45 Gs would be lethal within seconds without support, crushing your internal organs and causing hemorrhaging throughout your body. But it's nowhere near the extreme gravitational environments near neutron stars or black holes. As you fall deeper into the star, something interesting happens. The gravitational acceleration doesn't keep increasing. In fact, it decreases. This seems counterintuitive. Shouldn't gravity get stronger as you approach the center? The key is the shell theorem, proven by Newton. For a spherically symmetric mass distribution, the gravitational force at any point inside the sphere is determined only by the mass at smaller d. The mass in the shells outside your current position doesn't contribute. As you descend toward the center, there's less and less mass beneath you pulling you down, so the gravitational acceleration decreases. reaching zero at the exact center. For our red dwarf with relatively uniform density, actual red dwarfs have density increasing toward the core. But let's simplify. The gravitational acceleration at radius r inside the star would be gr equals gmr times where r is the total radius. This means g decreases linearly from 440 meters per second squared at the surface to 0 meters per second squared at the center. At the halfway point, 100,000 kilometers from the center, gravitational acceleration will be about 220 meters per second squared, still 22 times Earth gravity. But half the surface value. What about tidal forces, the differential gravitational force across your body? These are what cause spaghettification near black holes, where the gravity at your feet is so much stronger than at your head that you're literally stretched into a long, thin stream of atoms. Tidal force scales as to gm times h r cubed, where h is your height. For a 2-meter-tall human at the surface of our red dwarf, tidal force approximately equals to times 6.674 times K minus 11 times 3.978 times 1029 times 2 times Ke cubed approximately equals 1.3 times 10³ meters per s squared equals 0.0013 meters per second squared. This is negligible, about 0.00013% of the gravitational acceleration at your feet. You wouldn't feel any stretching at all. Tidal forces on a red dwarf are mild because, while the star is dense, it's not extremely compact. The radius is large enough that the gravity gradient across human scales is minimal. Compare this to a neutron star, where tidal forces at the surface would exceed thousands of Gs per meter. There, you'd be spaghettified instantly. The red dwarf, by contrast, destroys you through other means: heat and pressure, not tidal forces. Your terminal velocity, the speed at which drag force equals gravitational force, increases as you descend into denser plasma. In the outer corona with negligible density, terminal velocity would be essentially infinite. You'd just keep accelerating. In the photosphere, with density around 10 to 7 kilograms per cubic meter, drag would still be minimal at your mass and velocity. But deep in the interior, with densities exceeding 100,000 kilograms per cubic meter, 100 grams per cubic centimeter, drag becomes substantial. Using Stokes' law for a sphere moving through viscous fluid, F_drag equals 6 where eta is dynamic viscosity, r is your effective radius, and v is velocity. For stellar plasma at interior conditions, effective viscosity is complex. It's not a simple fluid, but estimates suggest that any macroscopic object would reach a terminal velocity of just a few meters per second at most in the deep interior. Of course, by the time you reach the deep interior, you're no longer a macroscopic object, you're a cloud of ionized atoms. But those atoms would still settle into convective flow patterns, moving at the typical convective velocities of meters to tens of meters per second. Now let's discuss the mechanism that actually destroys you. Heat. The journey from normal human body temperature 37 C, or 310 Kelvin, to stellar interior temperatures millions of Kelvin, involves passing through every phase transition and chemical breakdown threshold matter can experience. Phase 1, survivable heat 300 K to 400 K. At 310 K, you're alive and normal. By 315 K for DC, you have a severe fever. Proteins are beginning to denature. At 320 K for 7C, enzymes are failing and prolonged exposure would be fatal. At 330 K 57C, most proteins denature irreversibly. Between 330 and 373 K 100C, water in your cells begins to boil, cells rupture, and death is certain within minutes. This phase would occur in the outer corona, before you even reach the transition region. Even though the coronal plasma temperature is over 1,000,000 Kelvin, the low density means heat transfer is initially slow, but radiative heating from the bright photosphere below ensures you'd reach lethal temperatures within minutes at most. Phase 2, organic destruction, for 100 K to 1000 K from for 100 K 1 to 7C to about 600 K 3 to 7C. All organic matter undergoes pyrolysis, thermal decomposition. Proteins, lipids, carbohydrates, and nucleic acids break down into smaller molecules. Your body would char, then burn, then break down into simpler organic compounds like methane, carbon monoxide, and eventually just carbon dioxide and water vapor. By 600 to 800 K. Even these simple organic molecules decompose. Water dissociates into hydrogen and oxygen. Carbon dioxide breaks into carbon monoxide and oxygen. By 1000 K 7 to 7 C, all molecular bonds involving carbon, nitrogen, and oxygen compounds have broken. You're reduced to simple molecules, H's, ON, CO, and eventually just individual atoms. This phase occurs in the chromosphere and lower photosphere. The time scale depends on heat flux, but at typical chromospheric conditions, complete molecular decomposition would occur within seconds. Phase 3. Atomic ionization, 1000 K to 10,000 K. Between 1000 and 10,000 K. Molecules dissociate into atoms and atoms begin to ionize. At 3000 K, molecular hydrogen H's dissociates into atomic hydrogen H. At 5000 K, metals like sodium and calcium lose their valence electrons, becoming singly ionized. By 10,000 K, the temperature at the base of the photosphere hydrogen begins to ionize significantly. The ionization energy of hydrogen is 13.6 electron volts, equivalent to about 160,000 Kelvin in thermal energy. But ionization occurs at much lower temperatures due to the Maxwell-Boltzmann distribution of velocities. Some atoms are always moving fast enough to ionize, even when the average energy is lower. This phase occurs throughout the photosphere and upper interior. By the time you're 10,000 kilometers deep, essentially all atoms in your body are ionized, at least singly ionized for light elements, like carbon and nitrogen, and multiply ionized for anything heavier. Phase 4. Complete ionization, 10,000 K to 1,000. 0 K. As temperature climbs above 10,000 K, heavier elements progressively lose more and more electrons. Carbon ionization energies 11.3 electron volts, 24.4 electron volts, 47.9 electron volts, 64.5 electron volts, 390.1 electron volts. For 190.0 electron volts loses electrons one by one. First singly ionized C, then doubly C, then triply C cubed. By 100. 0 K. The temperature at about 10,000 kilometers depth. Light elements like hydrogen, carbon, nitrogen, and oxygen are fully ionized. All electrons have been stripped away, leaving only bare nuclei and a sea of free electrons. By 1 million Kelvin, the temperature at 100,000 kilometers depth, even heavy elements would be highly ionized. If they were present, iron, for example, would likely be stripped of a dozen or more of its 26 electrons. This complete ionization is irreversible at these temperatures and pressures. You're no longer molecules, no longer atoms, just a collection of bare nuclei, protons for hydrogen, alpha particles for helium, bare carbon nuclei, etc., and free electrons, all moving at velocities of hundreds to thousands of kilometers per second. Phase 5. Nuclear domain 1 million K and above. At the temperatures in the core 2 to 3 million Kelvin, we're finally in the regime where nuclear reactions are possible. The nuclei themselves can now interact via the strong nuclear force through quantum tunneling. Hydrogen nuclei fuse into deuterium, helium-3, and eventually helium-4 for the hydrogen nuclei that were once part of your body. This is their ultimate fate, to participate in nuclear fusion, converting mass into energy and transforming from hydrogen into helium. This process will take billions of years on average for any given proton, but it's the end point of the journey. The heavier elements, carbon, nitrogen, oxygen, phosphorus, sulfur, don't undergo fusion at red dwarf core temperatures. They'll remain as bare nuclei, cycling through the convective zones indefinitely. If the star were more massive and could achieve higher core temperatures, these elements might fuse further: carbon into oxygen, oxygen into silicon, silicon into iron. But in a red dwarf, they're stable. Let's not forget radiation, electromagnetic and particle radiation that's bombarding you throughout. The journey starting in the outer corona and transition region. You encounter ultraviolet radiation, wavelengths from 10 to 100 nanometers, with energies from 3 to 100 electron volts. UV breaks chemical bonds and damages DNA. At moderate intensities like Earth's sunlight, it causes sunburns and increases cancer risk. At stellar intensities, it would strip electrons from atoms and break apart any remaining molecules within seconds. X-rays, wavelengths from 0.01 to 10 nanometers, with energies from 100 electron volts to 100 keV. X-rays penetrate deep into tissue, ionizing atoms throughout the body. At stellar intensities, especially during flares, X-ray doses would be millions of times the lethal threshold within minutes. Gamma rays, from fusion reactions in the core, though they're absorbed and downgraded to lower energies before reaching the surface. Gamma rays have energies above 100 keV, enough to shatter atomic nuclei in some cases, certainly enough to ionize any atom. The radiation dose can be quantified in Gray's energy deposited per kilogram or sieverts. Biological effect. A dose of 5 sieverts is lethal to humans. In the corona of a flaring red dwarf, radiation levels could easily exceed 100,000 sieverts per hour, 20,000 times the lethal dose. But radiation is almost irrelevant compared to the thermal destruction. By the time radiation has damaged your DNA and proteins, you're already experiencing temperatures that vaporize organic matter instantly. Radiation is just one of many mechanisms ensuring your destruction. Particle radiation, stellar wind, protons and electrons, plus heavy ions ejected during flares adds to the damage. These charged particles have kinetic energies from a few keV to many MeV. When they collide with atoms in your body, they transfer energy, creating cascades of ionization. But again, this is minor compared to the sheer thermal violence of the environment. The bottom line: by the time you've descended just a few thousand kilometers into the star, every mechanism of destruction has been exhausted. You've been irradiated with lethal doses of UV, X-rays, and particle radiation headed to temperatures that vaporize all organic materialized completely, with all molecular and atomic bonds broken, mixed into stellar plasma and subjected to pressures billions of times atmospheric acicleta, to convective velocities and dispersed throughout. The stellar interior offers no gradual death here. It's not like drowning or suffocating, where consciousness fades over minutes. It's instantaneous destruction on every level, molecular, atomic, and eventually nuclear. You cease to exist as an organized structure within seconds of reaching the photosphere, and within minutes subjectively, your component atoms are deep in the interior. Indistinguishable from the star itself, not all red dwarfs are created equal. Let's explore how falling into different types would change the experience. The smallest red dwarfs around 0.08 solar masses are just barely massive enough to sustain fusion. They're about 10 to 15% larger than Jupiter in radius, with surface temperatures around 1,000 to 2,300 Kelvin. Surface gravity would be lower, maybe 100 to 200 meters per second squared, making the initial fall slower. But the interior would be cooler and less dense. Core temperatures might only reach 1 to 2 million Kelvin, with pressures and densities proportionally lower. The fusion rate would be extremely slow. These stars shine with just 0.01% of the sun's luminosity. The convective timescales would be longer. It might take thousands of years for material to complete a full convective cycle, from core to surface and back. But the ultimate fate is the same: complete ionization and mixing into stellar plasma. Interestingly, the smallest red dwarfs are predicted to last the longest, up to 10 trillion years. So, if your atoms are incorporated into a minimal red dwarf, they'll be part of that star for longer than almost any other possible fate. At the other end, large red dwarfs around 0.5 solar masses are significantly different. They're about 50 to 60% of the sun's radius, with surface temperatures reaching 3,500 Kelvin. Surface gravity would be perhaps 1,000 meters per second squared to 100 times Earth gravity. The fall would be faster, more violent. The interior would be hotter and denser. Core temperatures might reach 10 million Kelvin, approaching the conditions in our sun's core. Pressures would be higher, densities greater. The fusion rate would be much faster. These stars can shine at 5 to 8% of the sun's luminosity. Larger red dwarfs also have shorter lifetimes, only tens to hundreds of billions of years, rather than trillions. They burn through their hydrogen faster, even though they're still far more efficient than sun-like stars. Age also matters. Young red dwarfs formed within the last few billion years are more active. They rotate faster, have stronger magnetic fields, and produce more violent flares. An older red dwarf, say 10 billion years old, would have spun down due to magnetic braking, would be less magnetically active, and would flare less frequently and less violently. Falling into a young, active red dwarf would expose you to more intense radiation from frequent flares. Falling into an old, quiet red dwarf would be relatively, and I stress relatively, with less dramatic magnetic activity. But the thermal and pressure destruction would be essentially the same. Age doesn't significantly change the interior conditions once the star has reached the main sequence. Let's imagine a science fiction scenario. You have an impossibly advanced protective suit, not just a space suit, a marvel of future technology that can withstand extreme temperatures, pressures, and radiation. How far could you descend before even this wonder suit fails? In the corona and chromosphere, the suit would need to reflect or radiate away enormous amounts of thermal energy. The temperature is millions of degrees, but density is low. Advanced multi-layer insulation, backed by active cooling systems using, say, liquid helium, might be able to handle this. You'd need to radiate waste heat, requiring large radiator panels that would glow white-hot. Through the photosphere, conditions worsen. Temperature is lower, but density is much higher. Heat flux, the rate of thermal energy transfer per unit area, increases dramatically. Your suit would need active cooling capable of dumping megawatts of thermal energy per square meter. That requires exotic cooling technologies, maybe direct matter to energy conversion, to power enormous heat pumps. At 10,000 kilometers depth, 100,000 K, 10,000 atmospheres, 10 grams per cubic centimeter, you'd need a suit that can withstand pressures equivalent to the deepest ocean trenches, while keeping the interior at survivable temperatures. The suit would have to be incredibly thick and strong, perhaps made of some sci-fi material, like exotic matter with negative mass, or force fields that redirect pressure and heat. At 50,000 kilometers depth, 500,000 K, 100,000 atmospheres, 50 grams per cubic centimeter. Even the most advanced materials would struggle. The pressure is so intense that ordinary matter would compress significantly. The heat flux is so high that radiating it away would require your suit to have a surface temperature of tens of thousands of degrees itself. It would glow like a star. At 100,000 kilometers, depth 1 million K, 1 billion atmospheres, 100 grams per cubic centimeter. We've exceeded anything plausibly protectable. The pressure alone would crush any atomic lattice-based material. You'd need something that doesn't rely on electron degeneracy for structural integrity. Perhaps exotic matter held together by strong nuclear forces, or a pocket universe separated from the stellar interior by a dimensional membrane. Even if we grant such impossibilities, what could you observe? The environment is completely opaque. Photon mean free path is centimeters. You couldn't see in any conventional sense. You'd be surrounded by uniformly glowing plasma in every direction, like being inside a light bulb. The only way to observe would be through instruments measuring temperature, pressure, density, magnetic fields, and particle composition. You could potentially measure temperature gradients to map convective flow's magnetic field, strengths, and topologies, nuclear reaction rates by detecting neutrinos which pass through your ship unimpeded, density via seismic measurements, detecting stellar oscillations, chemical composition via spectroscopy of the surrounding plasmane principle. A sufficiently advanced probe could survive in the outer layers, photosphere, and upper interior for some time, transmitting data before succumbing to the environment. This is actually being considered for future solar missions, sending probes to skim through the sun's corona and outer atmosphere to study conditions in situ, but descending into the deep interior and core, That's firmly in the realm of impossible, even with far future technology. The conditions are simply too extreme for any matter-based object to survive. You'd need something that operates on entirely different principles, maybe an entity made of force fields, or an artificial intelligence uploaded into a plasma-based computational substrate that could exist as part of the star itself. How does falling into a red dwarf compare to falling into other types of stars? Falling into the Sun G-type main sequence, 1 solar mass, 696,000 kilometers radius, surface gravity, 274 meters per second squared, 28 Gs, weaker than the red dwarf surface. Temperature, 5,778 K, over twice the red dwarf's temperature. Interior structure, distinct core, radiative zone, and convection zone. Core temperature, 15 million K, 5 times hotter than the red dwarf. Core density, approximately 150 grams per cubic centimeter, similar to the red dwarf. Fall into the Sun would be similar in many ways, but the internal structure would be different. You'd pass through the convective zone, then enter the radiative zone where energy transport is via photon diffusion rather than convection. The core would be much hotter and fusion would be faster, but the end result, complete ionization and incorporation into stellar plasma, would be identical. Falling into a blue giant B-type main sequence, 20 solar masses, 7 million kilometers radius, surface gravity, approximately 100 meters per second squared, 10 Gs, weaker than both the red dwarf and Sun surface. Temperature, 20,000 to 30,000 K, 10 times the red dwarf's temperature. Interior structure, convective core, radiative envelope opposite of smaller stars. Core temperature, 30 to 40 million K, 15 times hotter than the red dwarf. Core density, approximately 10 grams per cubic centimeter, lower than both red dwarf and Sun. Spread over larger volume. The fall into a blue giant would involve much higher surface temperatures, meaning thermal destruction would occur earlier in the descent. The internal structure is inverted compared to smaller stars. The core is convective, due to the high temperature dependence of fusion rate, while the envelope is radiative. The core is also much hotter, capable of fusing helium into carbon and oxygen via the triple alpha process. Falling into a red supergiant M-type supergiant, 10 to 20 solar masses, 500 to 1,000 solar radii. This would be bizarre. Red supergiants are so large and so diffuse that their outer layers are barely denser than the best vacuum we can create on Earth. You could fall for weeks through the outer atmosphere before reaching conditions dense enough to be noticeable. Surface gravity might be just 0.01 meters per second squared, 0.001 grams. You'd barely feel any pull at all. But eventually, you'd reach the core, a compact, superdense region where helium and even heavier elements are fusing. The core might be sun-sized, but with density and temperature rivaling neutron star conditions. The contrast between the tenuous envelope and the extreme core would make for a strange journey. Mostly gentle descent through thin gas, then suddenly encountering an environment more extreme than anything in a red dwarf. Falling into a neutron star, 10 kilometers radius. 1 point for solar masses. This is where things get truly extreme. Surface gravity would be about 2 km per second squared to 100 billion Gs. You'd be accelerated to about 1/3 the speed of light by the time you hit the surface. Tidal forces would be thousands of Gs per centimeter. You'd be spaghettified long before reaching the surface. The surface itself is a crystalline lattice of atomic nuclei, mostly iron at densities of 106 grams per cubic centimeter, with temperatures around K, just beneath the surface. Nuclei merge into a neutron-rich nuclear poster of exotic phases. In the core, neutrons are packed so tightly that they might form matter quarks, the constituents of protons, and neutrons existing freely rather than bound into nucleons. Your atoms would be crushed out of existence. Electrons would be forced into nuclei, converting protons into neutrons via inverse beta decay. Your matter would be compressed into degenerate neutron matter, indistinguishable from the neutron star itself. This is a fundamentally different form of destruction than the red dwarf, not ionization and fusion, but compression into an entirely different state of matter. Falling into a black hole any mass, this is perhaps the most famous extreme environment. As you approach the event horizon, time dilation would cause your experience of time to diverge dramatically from that of distant observers. From your perspective, you'd cross the horizon in finite time, but distant observers would see you freeze at the horizon, your light red-shifting away to invisibility. Past the event horizon for a large black hole where tidal forces at the horizon are weak, you'd have some subjective time before reaching the singularity minutes to hours, depending on the black hole's mass. During this time, you'd be in a region of space-time so warped that all paths lead toward the singularity. There's no possibility of escape, not even in principle. Near the singularity, tidal forces would become infinite. You'd be stretched infinitely in one direction, and compressed infinitely in the other's ultimate spaghettification. And then, we don't know. Our physics breaks down at the singularity. General relativity predicts infinite curvature and density, but this almost certainly indicates that quantum gravity effects we don't yet understand become important. In comparison to these extremes, a red dwarf is almost gentle. There's no spaghettification, no relativistic effects, no exotic matter states, just straightforward, classical destruction by heat and pressure. In the hierarchy of stellar doom, red dwarfs are the entry-level option. This journey into a red dwarf isn't just a thought experiment. It teaches us fundamental lessons about the universe and how matter behaves under extreme conditions. First, we learn about the scale of energies involved in stellar processes, the binding energy of the Sun, the energy required to completely disassemble it into separate atoms. Spread across infinite distance is about 3.8 times 1041 joules. That's roughly the Sun's total energy output for 10 million years. Stars are incredibly strongly bound objects held together by gravity, and disrupting them requires energies beyond anything achievable with human technology. Second, we learn about the states of matter. We're familiar with solids, liquids, and gases from everyday life. We've created plasmas in laboratories and fusion experiments, but stellar interiors show us plasma under conditions that bridge the gap between ordinary gas and exotic quantum degenerate matter. The interiors of red dwarfs hint at the electron degeneracy that dominates in white dwarfs, without reaching full degeneracy. This helps us understand the full range of matter's behavior from the molecular structures of life, at moderate temperatures and pressures, through the ionized plasmas of stellar atmospheres, to the quantum-dominated regimes of degenerate matter in white dwarfs and neutron stars, and ultimately to the quantum gravitational realm near black holes. Third, we learn about energy transport and timescales. A photon produced in the core of a red dwarf takes tens of thousands of years to random walk its way to the surface, being absorbed and re-emitted countless times. This is why stars have thermal inertia. They can't change their structure quickly. If you somehow turned off fusion in a star's core, it would take thousands to millions of years for the change to become apparent at the surface. Understanding these timescales is crucial for stellar evolution models and for interpreting observations of stars at different ages and stages of life. Fourth, we learn about the universality of physical laws. The same quantum mechanics that governs electron behavior in atoms on Earth also explains how electrons in stellar cores create degeneracy pressure. The same thermodynamics that describes heat engines governs energy transport in stars. The same nuclear physics used in fusion reactors explains stellar fusion rates. The universe operates on the same laws everywhere, from the smallest scales to the largest. Studying extreme environments like stellar interiors tests these laws at their limits and increases our confidence in their universal validity. Looking forward, red dwarfs will dominate the universe's future in ways that more spectacular stars never could. In the relatively near future, say 1 billion years from now, many of the brightest stars in our current night sky will have died. Massive stars like Rigel, Betelgeuse, and Spica will have exploded as supernovae. Medium-mass stars will be entering their red giant phases. The galaxy will be perceptibly different, but red dwarfs will be essentially unchanged. A red dwarf that formed 1 billion years ago has barely aged at all. It will still be on the main sequence, still fusing hydrogen, still looking almost identical to when it formed. In 100 billion years, when the universe is 7 times its current age, galaxy formation will have essentially stopped. The cosmic expansion, driven by dark energy, will have isolated galaxy clusters from each other. The Milky Way will likely have merged with Andromeda and the other local group galaxies, forming a single large elliptical galaxy. Most of the gas available for star formation will have been consumed. Star formation will drop to a tiny fraction of current rates, but the red dwarfs formed in earlier epochs will still be burning. Most of them will have barely aged. They'll be the dominant source of light in the galaxy by sheer numbers. They already are. But in the far future, they'll be essentially the only sources of light besides white dwarfs and occasional. In OVAE. In 1 trillion years, when the universe is 70 times its current age, star formation will have essentially ceased. The last stars will have formed from the last scraps of available hydrogen gas. The universe will be entering the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars and black holes. But red dwarfs will still be shining. The smallest ones will be only 10% through their lifetimes. They'll continue to dominate the universe's light budget for trillions of years to come. In 10 trillion years, the first red dwarfs will finally be exhausting their hydrogen fuel. These ultra-long-lived stars, the smallest ones, at 0.08 to 0.1 solar masses, will begin to evolve off the main sequence. But even their death is gentle. They'll simply cool and contract, forming helium-white dwarfs without any dramatic fireworks. By 20 to 30 trillion years, most red dwarfs will have died. The universe will be profoundly different. Galaxies will have evaporated as stars are ejected through gravitational interactions. Stellar remnants will dominate. The universe will be dark and cold, but a few red dwarfs, the very smallest, the most efficient. The ultimate survivors will still be burning. These will be the last natural light sources in the universe, the final campfires as the cosmos fades to black dot, and then, finally, even they will go out. The last red dwarf will exhaust its fuel, cool into a helium-white dwarf, and the stelliferous era, the age of stars, will end. The universe will enter its long decline into eventual heat death, dominated by black holes slowly evaporating via Hawking radiation over Googolier timescales. This is why red dwarfs matter. They're not just stars, they're the stars that will witness the entire arc of cosmic history. From the first moments after the Big Bang, the oldest red dwarfs are nearly as old as the universe itself, to the final fading of the light trillions of years. Hence, there's something humbling and or inspiring about contemplating this journey. Falling into a red dwarf forces us to confront the sheer extremity of the universe conditions, so far removed from human experience that they seem almost fictional. Yet they're real, common, and fundamental to how the cosmos works. It reminds us of our fragility. We exist in an incredibly narrow band of temperature, pressure, and radiation levels. Step outside that band, whether into the cold vacuum of space or the heat of a stellar atmosphere, and we're destroyed quickly and completely. Our existence depends on the stability of Earth's environment, which in turn depends on the sun's stable output, which depends on the balance of forces in the sun's interior. We're products of stars. In a very literal sense, the atoms in our bodies, the carbon, nitrogen, oxygen, phosphorus, sulfur, iron, were forged in stellar cores through nuclear fusion, then dispersed into space when those stars died. We're made of stardust, as Carl Sagan famously said, but red dwarfs complicate this narrative. They create helium from hydrogen, but they never progress to heavier element fusion. They don't contribute to cosmic chemical enrichment the way larger stars do. In a universe with only red dwarfs, the complex chemistry needed for life might never develop. This suggests that the mix of stellar types is crucial for life. We need the short-lived massive stars to produce heavy elements through fusion and supernovae. We need the medium-lived sun-like stars to provide stable habitable zones for billions of years. And we have the red dwarfs as cosmic witnesses persisting across eons, perhaps hosting their own forms of life adapted to dim red suns. There's also something poignant about red dwarfs being invisible to the naked eye. The most common stars in the universe are our nearest stellar neighbors, the stars that will outlast everything else, and we can't see them without telescopes. The universe's true nature is hidden from casual observation. Only through scientific instruments and mathematical reasoning can we perceive the full reality. This is a metaphor for science itself, looking beyond surface appearances, using tools and theories to reveal underlying truths that aren't immediately obvious. Red dwarfs are a reminder that the universe is both stranger and more comprehensible than we might expect. Strange in the sense that most stars are invisible to us, comprehensible in that we can still study them, understand them, and even simulate falling into them through physics. And so our impossible journey ends, or rather, transforms. You began as a human being, standing at the edge of space, about to fall toward a dim red star. Through the course of this descent, you experienced the approach through the corona, where temperatures paradoxically rise to millions of degrees despite being far from the visible surface heat. Violent stellar flares that can unleash the energy of millions of nuclear weapons in second chromosphere, where hydrogen recombines and spicules erupt like cosmic fountains. Photosphere, the surface where the star becomes opaque and photons finally escape, after tens of thousands of years trapped in the interior. The convective interior, a churning ocean of plasma where entire stars' worth of matter circulates in ponderous loops. Over millions of years. The fusion core, where temperatures reach millions of degrees and hydrogen nuclei tunnel through the Calm barrier to fuse into helium, releasing energy according to E equals mc squared. Along the way, you were subjected to surface gravity 45 times. Earth's normal gravity temperatures rising from 2,500 Kelvin at the photosphere to 3 million Kelvin in the core, pressures increasing from near vacuum in the corona to 100 billion atmospheres at the center, densities climbing to 150 times that of water, denser than lead or uranium. Radiation doses millions of times the lethal threshold. Complete molecular disintegration, atomic ionization, and ultimately incorporation into stellar plasma. You didn't survive this journey in any meaningful sense, but your atoms did, and they became part of something far larger and longer lasting than any human life. A star that will burn for trillions of years, outlasting civilizations, galaxies, and perhaps even the concept of time as we understand it. Red dwarf stars are remarkable objects. They're the universe's ultimate minimalists, using as little fuel as possible, shining as dimly as necessary, but persisting for timescales that dwarf everything else. In a cosmos that often seems to favor the spectacular supernova explosions, gamma-ray bursts, colliding galaxies, red dwarfs remind us that sometimes persistence and efficiency are more important than flash and drama. They're also humbling. Despite being the most common stars in the universe, we've only been able to study them in detail for the past few decades. We can't see them with the naked eye. We don't have any in our immediate solar neighborhood bright enough to attract ancient astronomers' attention. Our entire understanding of these stars, that they exist, how they work, how long they'll last, is a product of modern astrophysics using sophisticated telescopes and theoretical models. This is science at its best, revealing the hidden majority, understanding objects so different from our experience that no amount of casual observation would uncover them, and synthesizing observations across the electromagnetic spectrum with physics developed in laboratories to create a coherent picture of how these stars live and die. The fact that we can simulate falling into a red dwarf, that we can calculate temperatures, pressures, fusion rates, and timescales with confidence, even though no human will ever make this journey, is a testament to the power of mathematics and physics. We can understand environments utterly hostile to life, using principles developed in environments comfortable for life, and perhaps most remarkably, red dwarfs might host life themselves. Despite their violent flares, their dim light requiring close planetary orbits, and the tidal locking that would create permanent day and night sides on planets, there's a possibility that life could adapt to these conditions. If it can, then the universe might be full of life we've never imagined, life adapted to crimson skies, life that has billions of years for evolution to work. Life that will still be flourishing trillions of years from now when our sun is a cold white dwarf and Earth is a frozen, lifeless rock dot. And that brings us to the end of this cosmic journey, fellow explorers. We've fallen into a red dwarf, experienced destruction on every possible level, and emerged with a deeper understanding of these remarkable stars and the extreme physics that governs them. If you found this journey fascinating, if you learned something new, or if you're just amazed that we can understand the universe in this much detail, do me a favor, hit that like button. It tells YouTube that science content matters and helps us reach more curious minds like yours. And if you're not already subscribed to the Cosmic Atlas, what are you waiting for? We've got dozens of cosmic adventures planned, from journeys into black holes, to explorations of the early universe, to investigations of the strangest objects in space. Subscribe and hit the notification bell so you never miss an episode. Share this video with anyone who loves space, physics, or just incredibly detailed thought experiments. This is the kind of content that makes people fall in love with science, and every share helps us grow the community of cosmic explorers. I want to hear from you. What stellar object should we explore next? Should we fall into a neutron star and experience the most extreme gravity this side of a black hole? Should we dive into a supermassive black hole at the center of a galaxy? Should we ride along with a gamma ray burst, the most powerful explosion in the modern universe? Leave your suggestions in the comments below. The best idea might become our next adventure. Before I let you go, I want to leave you with one final thought. The atoms in your body, the carbon, nitrogen, oxygen, iron, all of it came from stars. Not from red dwarfs, since they don't create heavy elements, but from larger stars that lived, fused heavier elements, and died in supernova explosions that seeded the galaxy with the raw materials for planets and life. In a very real sense, we're made of the ashes of dead stars, with the universe waking up and looking at itself. And when we study stars, when we calculate what would happen if we fell into a red dwarf, we're using brains built from stardust to understand the furnaces that created that stardust in the first place. That's not just science. That's poetry. That's meaning. That's why we explore the cosmos, not just to satisfy curiosity, but to understand our place in the grand cosmic story that stretches from the Big Bang to the heat death of the universe trillions of years from now. Thank you for joining me on this journey into a red dwarf star. Until next time, keep looking up, keep asking questions, and keep exploring the incredible universe we call home. This is the Cosmic Atlas, reminding you that the universe is vast, strange, beautiful, and noble, and the adventure is just beginning. See you among the stars.